as we get ready for our next speaker, and we're going to dive into the field of connected metrology, so characterizing complex layer stacks along the manufacturing chain. And our next speaker used to work in R&D as a project manager lead, but is now changing his perspective on the matter of things, and is product manager of EPICS. We are giving the stage to Johannes Zettler from LATEC.
Thank you, Janika. Hello, everyone. To those of you who do not know LATEC, let me introduce LATEC very quickly. LATEC is a company from Berlin, Germany, and we provide optical process-integrated optical metrology for semiconductor industry, but also for photovoltaics and large area coding. Today I will focus on our metrology for the compound semiconductor industry, specifically the power electronics. And as our topic today is the challenges of the semiconductor industry in the next few years, we have asked ourselves which challenges are impacting us as optical metrology most. And no surprise, these challenges have already been named today. One is a tool matching, fab matching issue, the diversification of global supply chains, the movement towards more resilience gives the necessity to improve the process matching and just improve our metrology tools. And the second one, we have already heard as well, for GaN power devices, Dilder said we have 10 years of improvement coming up. And some part of this improvement, as we've heard, will be the increasing complexity of the devices, of the epi layers. And we will have increasing number of layers, more complex layer structures, and tighter specifications for individual layers. And how we want to cope with that is the topic for today. So let's start with the metrology that LATEC provides for compound semiconductor industry. We've started out with in situ metrology in epitaxy, where we have the EpiCurve DT, an optical metrology tool that measures the reflectance at multiple wavelengths, the temperature, and the local curvature of the wafer during the epitaxial process. And we have also the EPICS tool, which is a white light reflectance and photoluminescence mapping station, and the Triton, which is again an in situ product measuring or providing metrology for plasma etching processes. If you look at the front end process of such a structure, the EpiCurve DT and the Triton have the dedicated positions within the process, and the mapping station can be used in various parts of the manufacturing process. So far, our customers use all these tools individually, and they provide valuable information to them. When we just heard that the common question from the customer is, can you measure this? Can you measure this at this precision? And with structures getting more and more complex, to keep on being able to answer this question with yes, we can, we need to connect our metrology to generate synergies from complementary metrology methods that we have in our portfolio. And connecting this data yields us, for example, an improved die-resolved statistical process control for the individual layer structures, improved etching accuracy, or a higher accuracy for determining the optical material data for stack and device simulation. Let's look a little more into detail on the SPC. So what do we want to achieve with the connected metrology? In the end, we want to have a full quantification of the critical epi layers on the die level, meaning the layer thickness, layer composition, layer strain, for example. How do we get there? Well, we need to characterize the wafer in 3D in full 3D and then transform that into a dye matrix. First part is a difficult one. And we can only achieve that by combining in situ epi metrology with ex situ 2D wafer mapping. Why is ex situ wafer mapping itself not sufficient for the full 3D characterization? Well, when we measure ex situ only from the top, the depth information, the z direction or growth direction, is usually partially blocked or disturbed by upper layers. The one very keen example, for example, is a VCSEL structure where you grow a mirror on top. And when you have a mirror on top, it's very difficult to see everything that's below there. So we need to find a different angle to look at the depth, and that's where in situ metrology comes into play. So typically, the wafer is measured in a process 3 times by 3 products from us, and they derive data. In a customer MES, this data may be already collected, but the individual tools do not yet profit from the results of other tools. And that's the difference that we have with connected metrology if we then feed the data back into our tools. So not only the amount of information increases, but it is also combined for improved analysis in downstream processes. And that's nothing that we can only do LaTeX only, but as we have this database with partnering companies like Panalytical, we can also, where they have complementary measurement methods with sensitivities to other layers, maybe thinner layers, they can take advantage of this and provide then complementary data for the full stack description. So let's run through this process of connected metrology for our topic of today, the GaN-on-Si HEMT production. We've heard already it's a very complex stack. It's getting more and more complex. We have very thin layers that we need to analyze. And we will go to higher or to larger substrates where we have then very extreme requirements for uniformity both in epi and later on also in etching. So step 1 is in situ metrology during the epitaxy. In a typical planetary reactor, here we see a 5 by 200 millimeter silicon reactor. The wafer passes our optical metrology every 2 seconds. So in the wafer center, we have every 2 seconds a measurement of temperature, a measurement of reflectance at multiple wavelengths, and of the local curvature. As a typical growth time takes a few hours, we collect lots of data. And the important method here, or important information here is that as we're measuring during growth, we're always probing the currently upmost layer, and thus our sensitivity of the in situ measurement is unchanged from first to last layer. So how does the data look that we acquire during measurement? We have here a typical GaN-on-Si HEMT structure, and we see here. So we see here a schematic of the structure with the growth direction, and at the same time we acquire the data. And that we see for reflectance, we see here the reflectance at 2 wavelengths, for example. We see these oscillations, and these oscillations allow us to derive the critical parameters like growth rate, from which we can later on deduce the layer thickness or also the optical properties and composition. And with the curvature measurement that we see down here, we have an access to the local strain in our samples. So with analysis functions, we can thus derive from this measurement data the stack description, and we have suitable analysis function, advanced analysis functions for all these different layer types that we grew, or that our customers grow. And also with the layers getting more complex, more thinner, we also need to enhance the in situ measurement itself. For example, we have introduced shorter reflectance wavelengths recently to be able to analyze thinner layers with high aluminum content, or we have developed advanced analysis algorithms such as multi-layer analysis, multi-wavelength fits, gradient analysis that allow us to really analyze these layers and quantify the stack. Well, as the wafer passes our metrology tool, we also have measurements across like across the radius of the wafer, and just can perform the same analysis that we have done in the wafer center on the entire radii, on all the radii. We do not have an azimuthal information, but in the end we obtain the wafer stack in R direction and in growth direction in Z direction. So this is what we get from the in situ measurement already. And we can use that and put it to use in our ex situ measurement. So step 2 then is the ex situ white light reflectance mapping with a latex apex mapping station. Depending on the configuration, we are able to map their to do their spectral reflectance mapping between 250 and 2400 nanometers. And the goal here is in the end to obtain this full XY quantification of the critical layers. So first of all, let's look at the structure, and we need to see what are we actually measuring. For that, we simulated the reflectance of the typical HEMT structure we've seen before. And during the reflectance, we can also simulate the electric field inside the stack. And you see here, for example, this is a log scale, so it really, so in this region here, below the gallium nitride band gap, the light does not really penetrate much into the stack. And all our reflectance signals that we see in the wavelength region up to 260, roughly 260, is defined by the upmost layers, which are the critical layers in the HEMT stack. Whereas when we go above the band gap, we see that because all of these materials are transparent in this wavelength region, we see that the light penetrates really down to the substrate, and all that we have left here is basically Fabry-Perot oscillations. So we have the spectrum here at the center that you see here. The Fabry-Perot oscillations are in this region, and the peak here that we see here is in the UV region. Simulations show that this peak is very well correlates to the argon barrier, so aluminum content in the argon barrier. So, and one other thing to illustrate it, if we cut through the wafer here, we get this profile for the wavelengths that we have here, which is 320 nanometers. And if we look at it again for all wavelengths that we see here, and for the short wavelengths, we have a little contribution dominated by the upmost layers. And for the longer wavelengths, we have the Fabry-Perot oscillation. We see already here the inhomogeneity of the sample in X direction. And this we can use to have an access to the total thickness variation of our stack, which is dominated by the buffer because that's the thickest layer. So when we have that, we can have selected the UV region as a suitable wavelength region to determine our critical layer properties. And what's left in the end is then spectral fitting. And in order to be able to do spectral fitting with high precision and with high precision, we need to have a good ratio between measurement data and degrees of freedom. And ex situ measurement itself cannot provide this because there's still too many layers participating. But if we can take the data from in situ measurements, where we have already the depths, the Z information, so the stack information with R, so with the radius on the radial position on the wafer, we have a very good starting point for spectral fitting. And for non-critical layers, like for example the p-GaN layer, we can also decide that we do not need to fit this and just reduce the degrees of freedom. And thus we are able, for the critical layers, to do the spectral fitting. Here we see it for barrier composition and thickness. and just obtain these results on the 2D level. So to summarize the VL mapping part, we combine the in situ analysis with the ex situ mapping and just get a full stack 3D description of our wafer. And the critical layers, we have this really an X, Y accuracy for every point on the wafer. In the non-critical layers, we are on X, R in dimensions. And the last thing then is to convert it to die level. And that's one of the features of the EPIC software. Our customers can define and apply custom die patterns to the wafer map. They will obtain their resulting analysis information on the die level. They will obtain yield information on the die level. And they can also rotate or modify the die pattern to improve the yield, for example. And thus, we have in the end, and with that, I come to my last slide. By connecting the measurement tools that we provide, we can thus achieve in the end the die-resolved structure configuration, structure quantification for these critical layer parameters. And one last point I want to stress, the method presented here for GaN silicon HEMTs is an example, but also valid for many other types like VCSELs, micro-LEDs. Thank you for your attention.
Well, thank you, Johannes. Thank you, very insightful talk. You can join us here at the table again. And you recently switched positions and you're now product manager of one of the LaTeX products called EPICS. That means you're also forward-looking. What are you looking forward to when it comes to the roadmap of this new product? What are you excited about?
Many things. Before I was R&D project manager for the exact same project. So it's kind of my third baby, and I want to see it grow up. There's already mapping tools out there, and we didn't want to just go there as two, but we want to bring some new thing to the table. And I think we've showed here that with a stress or we focus, for example, on very accurate measurement, and with that, and combined with the in situ data, we can really bring some new insights and some additional benefit for our customers.
But that's now.
That thing happening.
And if you look at the next 12 months, what are you going to launch with EPICS, for example? Are any new things coming up in the near future?
Well, the UV part is something we're working on to make that more product, to finalize the UV part. So there's many small parts that we're working on. Yeah, but also the connected metrology is something we have to work on with the customers together. Yeah. And that's something that will keep us busy. Yeah.
Okay, nice.
I think that's the fascinating part, right? Yeah. That you sit here from an industrial supplier and from a metrology supplier as we sit here, and in the end, in the future, that has to continue to come together. Yeah. Because new technologies will come, we need to provide the systems to be able to do the measurements, the analytics, the metrology tools, and so that the roadmaps should be known to each other in that sense, right?
Yeah, exactly. Yeah. So if you look at connecting different types of metrology and working together there, why isn't everyone doing that already, Lars? It seems like a no-brainer.
Yes, but there is corporate boundaries.
Oh.
So yeah, it's not so easy to just say, hey, let's work together. Mm-hmm. So that's number one. Number two is, of course, everyone wants to have the profit for his own corporate, right? Again, there is some motivation to do it alone, if possible. But yeah, we reach boundaries, and at some point the pain or the pressure from the industry is high enough, so people start working together, and some work together already, but it's also not an afternoon project to do that, right? You need
if it were simple, it would have been done by a lot of...
Yeah, a few things have been done already, small things here, small things there. But yeah, it's niche-based often, and if you want to come together properly, that takes a different approach.
And if you then decide, okay, I want to combine different metrology types, what do you have to take into account? I know it's been happening for the last decade, but what are the topics that you need to think of when you are addressing this topic?
Yeah, for example, if you take a LaTeX tool, the contrast is set by the difference in optical refraction. in refraction, let's say, at the optical wavelength. And when you take, for example, X-ray reflectometry, there the contrast is set by the electron density, which is related, but not quite the same place where the boundary is. So you will get two slightly different values. Yeah. And you will have to have a model which makes sense of these two different values, because the model will tell you, okay, this is where the optical contrast for visible light will change, and here is the density change, and they are, let's say, 2 angstrom apart.
So you're painting a picture with different techniques, and you have to know where the difference lies to understand it.
Exactly.
Yeah. Is there anything you'd like to add then, Johannes?
Well, yeah, it's true, basically. No, I would just repeat the same thing. So.
Then nothing to add. Okay. When you look at Nexperia, for example, and how you guys do that across the different sites you have across the world, can you explain a bit how that works for you guys?
Obviously, we have got several fabs across the globe, and obviously we have got all these usual suspect tool suppliers that we use for our SPC control, process control, and all these things. And obviously looking into the epi, in particular for the GaN on silicon, and that's very interesting for us, obviously, is to understand, to know how we can have a better epi going forward. And yeah, we'll be watching this space.
We'll be watching this space. Okay. Did you learn anything new, Vesa, today from Johannes' talk?
I like this idea of there's lots of value to this kind of software development, basically, that you have basically probably had these measurement physical signals already in the past, but putting them into this kind of package that you can get the results from the single source, basically, instead of putting all the different measurement tool files together and doing lots of IT work. Or mesh integrated work to get different measurement data and somehow analyzing and combining it all together. So I like this approach of providing this kind of solution that gives answers, and then for the customer point of view, I guess it would be like easy to start using this data if it's providing repeatable results and combining several measurement results, and then start using it to this usual industrial means of process control and quality control, like the SPCs and such.
Yeah. Makes sense. I've got a question coming in from someone at Shakti Photon Solutions again, and I'm hoping I'm pronouncing this right. But can you comment on oxide-based 2-DAG electronics based on lanthanum aluminate and strontium titanate compared to GaN 2-DAG? Now, well, something like that.
As I'm informed, we have not measured these kind of samples yet. But feel free to ask, to contact us, and we're always happy to do demo measurements and show what we're capable of.
So we'll see if we can make a connection there. Yeah,
that is something that is very hot in this region, actually, because the University of Twente is very big in this oxide electronics research. Yeah. I also had the pleasure to go there and work a bit with these people. And when I look at this field, it looks extremely promising. Oxides, gallium oxide, we just had a discussion on the Ale. There is a lot of potential, but probably in 10, 15 years. So it's a bit about where gallium nitride is 15 years ago. Yeah. You still have issues with the substrates. If you look at them in an X-ray machine, they don't look quite homogeneous enough yet. Mm-hmm. But if they solve the substrate problem, obviously it's a rich class of materials with lots of possibilities, ferroelectric options, piezoelectric options. Yeah. That makes a lot of sense to do research on, but it's not yet there for the industry.
I liked the way you say it. Okay, if they solve that bit of the problem, then it's the next big step for the industry. Yeah,
sure. It's interesting. It's highly interesting. So people rightfully people put a lot of money in it.
Yeah, makes sense. Okay. Anyone a question for Johannes still? Everything clear?